So this is not Norway, this countryside here. This is northern Washington state in USA, close to the Canadian border. And you can see the countryside is a little bit similar. So this is a lake, not a fjord, but we have fjords. And so many similarities. We really like Norway. And I'm enormously grateful to the Kavli Foundation, the Norwegian Academy of Sciences, for the prize, and to Fred Kavli himself. Quite a visionary. What a wonderful tradition he started, and we're very grateful to have been recipients of this. So what I'd like to talk about today, this is slightly poetic title, Hearing the Sound of One Atom, but I hope that I can persuade you by the end of the talk that we can see the vibrations of one single atom now with the instrumentation that we now have. And so that really is a superpower. If you remember Superman back in the 1930s, 1940s, he had X-ray vision. In the 21st century, he'd do much better with electron vision, because with that, we can do things like hear the vibrations of one atom. So how did it come about? Let's dive into the talk. I want to address some of the key questions that we had for developing analytical electron microscopy. So what you've had in the previous three talks is heavily focusing on the elastically scattered electrons that carry information about the shape of the sample. But it's a little bit like black and white photography. There is no color in there. And I want to go into the color dimension. Why do different parts of the sample produce different spectroscopic signals, and what can we learn from those? So there were 4 milestones on the road to doing modern analytical electron microscopy, and when we ticked off all 4 of them, we got to the point where we could do atomic resolution imaging and chemical analysis. And with 2 more milestones, we got to vibrational spectroscopy in the electron microscope. And my second half of the talk is going to be dedicated to that. And that's really going beyond what the Kavli Prize was for. That was for aberration correction, not necessarily the applications to vibrational spectroscopy. And then, of course, a summary. So the whole talk can be also summarized as Ruska and Knoll microscope, 1931, 2 lenses, about 5 power supplies, magnification of 17.4 times. So not exactly the world's best high-resolution microscope, but it showed that you could combine electron lenses and concatenate the magnification. And just 2 years later, Ruska and Knoll estimated that electron microscopes would get down to a resolution of 2 angstroms eventually. So they were only off by a factor of 2 back 90 years ago. The more modern electron microscope, 2022, we have something like 70 lenses if you count all the quadrupoles that go into the column, and the monochromator down here and the spectrometer at the top. They need about 500 power supplies, because to make a good quadrupole, you need to throw in a bit of a sextuple, or particularly an octupole, without a sextuple to compensate the sextuple moment that the octupole is generating. Is not an octupole, it's actually more a sextuple than an octupole. So there's each stage in the correctors tends to have an octupole, a sextuple, and a quadrupole, and a dipole. And they're all rotatable, so that takes 8 power supplies just from one stage in a corrector. There is an awful lot of power supplies, but it's all computer controlled, and the user doesn't see it. The computer takes care of the alignments. It resolves atoms with ease. It determines their chemical type and bonding, and it can even hear the sound of a single atom. So how did it come about, and what was my motivation for going into this? As a postdoc straight after my PhD, I went to Japan, because at that time they had the world's highest atomic resolution electron microscope in the laboratory of Professor Kobayashi, who had a good sense of humor, so he called it his harem. And his harem was producing images of this kind of quality here's a 2 angstrom point-to-point resolution image of a grain boundary in germanium. And when we got this image, we said, hey, look, there's some brighter points at the grain boundary, and there's a lot of twinning planes. So this was just a couple of crystals of germanium that grew together. We deposited, co-deposited with gold. This came along. And so if we concentrate on where the bright spots are and make a guess that the bright spots correspond to larger tunnels through the germanium structure, we can come up with a model like this, where each bright dot corresponds to a 7-fold ring at the grain boundary, interspaced by 5-fold rings. And that turns out to be an arrangement which avoids dangling bonds in the germanium, which costs you a lot of energy. So we were basically exploring the atomic resolution in a germanium grain boundary back in 1977, and this is how far the microscopy could be pushed. Now, this was a 500 kV microscope. The followers were 1 million volt machines. They pushed the resolution down to close to one angstrom, but they produced a lot of radiation damage, and the latter models cost about $80 million each. So this was not a practical way for electron microscopy to go forward. And it was still the black and white world of the structure, and I got interested in the color world of determining the spectroscopic properties. So atomic resolution could be studied at that level, but we had no idea what species the atoms were. So if we had some gallium or arsenic or even gold sneaking into the structure, we would not have been able to see it. Back in the late 1970s, there was a couple of workshops at Cornell University on analytical electron microscopy. We started being able to form very small probes to do the analysis with, and we started having a whole range of detectors that could pick up analytical signals. So basically, to summarize what was going on, could we go from black and white world to the color one like this? And the answer was yes, by detecting analytical signals that go beyond where are the atoms and tell us what are the atoms and what are their properties. So quick review of the analytical signals. I think all microscopists in this room will be familiar with it. We have in the STEM, the primary signal tends to be high angular dark field imaging, which is the electrons deflecting close to the atomic nucleus to large angles. You catch it on an annular dark field detector, and it tells you that there was a heavy atom here. And the intensity of that signal actually weighs the atomic nucleus. We have inelastic scattering by the sample's electrons, smaller scattering angles, but energy losses which we can analyze, and they tell us what kind of atoms we had. We can look at the wavefront distortion, and in the STEM we usually look at how it deforms the ronchogram. In conventional transmission electron microscopy, it's used for phase contrast imaging, and it's the favorite signal of the conventional TEM technique. And we can also analyze the inelastic scattering that comes when the electrons set off vibrations of the nuclei, and there's a couple of ways they can mediate the energy can be transmitted, and I'll cover those as well. And we have the inelastic scattering processes deposit energy into the sample, and that energy can come out later. One way is secondary electrons. That was an excitation down here, and an electron popped out. You can have Auger electrons that come from de-excitation of an inner shell around the atom, and then an outer shell electron pops out. We can look at X-rays coming out from the de-excitation process, and we also have optical UV and infrared photons. The spatial resolution for these is typically not good enough to resolve atoms, but these signals over here, we can actually resolve the atomic signal with atomic resolution too. So there are many, many signals available, typically atomic resolution, and this is what makes the analytical electron microscopes really powerful and really interesting. So several milestones on the road to analytical EM. The first one was EELS. 1943, Hillier at RCA in New Jersey introduced the first electron energy loss spectrometer coupled to an electron microscope. There were other before, but they were more scattering chambers without any imaging capabilities. And so EELS looks at characteristic energy losses. If you're ionizing the K shell of a carbon atom, you need at least 285 electron volts of energy, and so there's a characteristic edge, carbon K. Oxygen K takes 530 volts, so here's a spectrum showing that the sample they were looking at has a carbon and oxygen in it. It's a very primitive spectrum, 10 volts energy resolution, very poor signal to noise ratio. We can do a lot better nowadays, but it was a start similar to the first microscope that Ruska put together in Berlin. But it didn't go anywhere because they had dirty vacuum system. With a dirty vacuum system, electron beam accretes carbon atoms onto the surface of the sample. So this was a very good machine for analyzing the contamination, but not so much the sample. And it took cleaner vacuum in electron microscopes in 1970s before this technique could really take off. Milestone number 2, Albert Crew and co-workers, students like Mike Isaacson and Joe Wall, put together what then to them was completely new scanning principle for electron microscope, scanning transmission electron microscope. It turns out that von Arden had a similar instrument in Berlin back in the 1930s, but you really needed electronic image recording. So electronics was not up to the requirements back in the 30s. It was in the 1970s, they produced the first images of single atoms in an electron microscope, and they had resolution about 2.5 angstroms. So it turns out they even had graphene in their microscope, but they could never resolve even the holes in graphene. So, but they did have monolayers of carbon, and then they could see how the intensity in the high-angle dark field image went from 1 to 2 to 3 to 4 quantized intensity, so it had to be graphene because amorphous carbon would never do that. And they could also do wonderful job on spectroscopy. So here's a spectrum of the adenine molecule recorded at 25 kV, low losses, lots of information right there. These kinds of capabilities are of great interest to material scientists and physicists, so STEM has really taken over for these two disciplines. For biology, the structure is more important. We struggle with the radiation damage. These signals are a bit weaker, so they require more radiation damage-resistant samples. So in biology, the CTM phase contrast is still kind of dominant. And also, so this acronym was pioneered back in the 70s. A new acronym has come along since, science, technology, engineering, and mathematics. So I always say that the STEM microscope is very good for STEM as a general field of study for people that want to go into science and technology. Milestone number 3, monochromated EELS. So there was this wonderful machine put together in Berlin by Boesch and Geiger, analyzer, monochromator, electron gun at the top, and it produced spectra such as this from amorphous silicon, 300 angstrom thick, prepared by decomposition of silane, primary energy 30 kilovolts. You can see all kinds of vibrations. So the high energy peaks are always due to hydrogen. And I'm not talking in wave numbers here. Infrared spectroscopists would like wave numbers, but just multiply the millielectron volts by a factor of 8, and you get the wave numbers. So these things at 400, they would be at 450. They would be somewhere around about 3,500 centimeters to -1 in a conventional spectrum. But I guess people working with electrons like millielectron volts better. And you can see a strong peak silicon-hydrogen bond. So the energy of these peaks is determined by the square root of the force constant for the bond divided by the effective mass. So heavy atoms give you energies which are lower down. Stronger bonds give you higher energies in a spectrum like this. So they basically open up a new world in the energy loss spectroscopy. And with a 30 kV beam, they should have been able to resolve something of the order of a few nanometers, but that was not their instrument. They had basically 0 imaging capabilities, and they got spectra from 30 micron areas, and they also had a very small acceptance angle, 10 to minus 4 radian. So they showed what could be done in principle, but the limitations of their instrument, particularly the small acceptance angle, meant that they could only look at the same kind of transitions that infrared spectroscopy can look at. What can be excited with light. And I visited Geiger's lab in Kaiserslautern in 1980 and discovered that this wonderful instrument was pushed into the corner, replaced by an infrared spectrometer. And the reason for that was that this instrument actually could not do anything that infrared spectrometer could not. And so, but that didn't exactly stop us from wanting to go further. And so this is a path that I'll be talking about in the second half of the talk. Milestone number 4, aberration correction. Here my job is very easy. You've just had 3 talks on the principles and the applications. So I don't need to go into it, except to say that in the STEM, we get better spatial resolution, and we also get more current in a given size probe, which allows us to do better analysis. So that is very important. 1997, we put together a proof of principle STEM aberration corrector back in Cambridge. Looks something like this. Here's the papers about it, the total schematic of the instrument. So we did 6 stages to give us a little bit more flexibility. We took a 25-year-old microscope, so we were not aiming for the world resolution record, but we wanted a proof of principle machine. Our funding was quite modest. We had $120,000, 80,000 pounds from the British Royal Society, and that was enough to build a proof of principle corrector like this. And the corrector is now on display in the Cavendish Lab Museum in Cambridge, UK, next to Deltrap's spherical aberration corrector and Hardy's CS and CC proof of principle corrector. So we owe a lot with our quadrupole octopole corrector to Deltrap's machine. He did it back in 1965, a proof of principle CS corrector. The Hardy's CS CC corrector has a lot of ideas in it that were later on taken up by CEOS, and the Max Hyder was showing you the SEM detector. They're not that different. It's not that different from Hardy's machine. And the results were not totally spectacular. Graphitized carbon, which could be captured in the uncorrected microscope at the large underfocus, became much clearer, and we resolved 2.3 angstroms in gold, but the fringes were very wiggly. We had a horrible sight, all kinds of instabilities, but it showed this thing is going to work. And the thing that made the difference is that we had complete control of parasitic aberrations up to 3rd order, and we had sufficient stability from the corrector itself, if not from the site. So that led us to design a corrector number 2. This one had 7 stages. It separated the quadrupoles and the octopoles so that the magnetic fields would not influence each other. There's a problem with the saturation characteristics of the magnetic materials. If you have a combined quadrupole octopole, if you excite the octopole, the quadrupole properties change. The strength of the quadrupole changes. So when we separated it out, a nice, easy to operate corrector emerged, and we put it into a more modern VGHB 501 STEM. The first one was ordered by Phil Batson, Yorktown Heights, and he showed very convincingly that the resolution improved about 2 times, and the beam current in the probe went up about 10 times. So here's Phil Batson, and here's his series of images, uncorrected, corrected, uncorrected. He's capturing a spacing of 1.9 angstrom in silicon, basically between these planes, 2 to 0. With aberration correction, the 1.36 reflection, that's what the distance between the atomic pairs, and he's even seeing below 1 angstrom reflections in the Fourier transform. More intuitively, this flat patch in the ronchogram shows the extent of the aberration correction, and that increased about 3 times in size. If you put the same, we put the same corrector, essentially the same corrector, into a 300 kV column, and that produced 0.78 angstroms clear separation of atoms in silicon in a different projection. So I think we can claim, and maybe there will be some opposition here from my colleagues, that we had the first direct images showing sub-angstrom structures in any type of electron microscope. So this was really convincing. The 1 MeV machines could not do this. This was a 10-year-old 300 kV machine, and I think it was one of the things that basically said to the microscopy community, aberration correction is here, follow it, is going to be really interesting. And this picture was taken by Matt Chisholm in collaboration with Pete Nellist. So, based on the fact that we now had a working corrector, but in a somewhat old-fashioned microscope that had a good cold field emission gun, but everything about it was not really up to snuff for aberration correction, we decided to develop a microscope by ourselves. We did this, we started on the project when the company had 3 employees, so we did not lack courage. But we did all kinds of saving measures, such as all our condenser and projector lenses are identical. Why design them differently? They're all lenses. Everything is completely interchangeable mechanically because these interfaces between modules are identical. The corrector was a nice sophisticated one that could do C5 correction now, so that was important to go further on resolution. There was a sample exchange and storage mechanism that decoupled the sample from the external world when we went into the microscope, which is good for stability. Lots of projector lenses, more quadrupole lenses to give flexible coupling into the EELS, ultra high vacuum at the sample, and the instrument was introduced in 2007 in the 100 kV version that still used the VG gun, and in 2010 with our own cold field emission gun at 200 kV. And here's the group that received the very first one. If you're in electron microscopy, the name of Christian Kolliaks is heavily associated with EELS. So this kind of a pattern, how a small company operates, we always worked in collaboration with leading laboratories in the field, and was very fortunate that these guys decided we want a Nion microscope. And in 2003, they really got a 2010, I beg your pardon, they got a world-beating machine. There was nothing equivalent at the time. So to illustrate the resolution improvement, 1 angstrom resolution of an atom. This is actually a badly taken picture. The pixel should have been smaller and the exposure time should have been longer. But we learned the technique for acquiring images, so it's much smaller pixels. 200 kV atoms 0.57 angstroms apart, nicely resolved. And you can see that there's no jitter in that image. You can't tell the scan direction, unlike cruise original image where the probe was scanning left-right. And you can see that when it was scanning this line, it actually wandered back onto the atom, even though it should have been outside. So these are the sort of instabilities that give you this jitter. Atoms tend to look a little bit squiggly in the stem, and that's because the sample or the probe are vibrating. So going from here to here, about 5 times spatial resolution improvement. That's a good number to remember. And again, Matt Chisholm took this image, and the probe current has improved very substantially too, otherwise you would not get a noise-free image such as this one. So this is completely unprocessed, no averaging, no nothing. So when you have a microscope like that, one of the things you can do is you drop the operating voltage, that's the Salva project, and you avoid direct damage to your samples if they don't have hydrogen. So if you have carbon, boron, nitrogen, it takes something like 20 electron volts to knock the atom out of the structure, and a 60 kV electron beam cannot supply that energy. So samples are very stable. You can illuminate one of these atoms with 10 million electrons, and it stays put. And if you take an image like this and you smooth it a little bit and run a line profile, you discover that the intensities of the individual atoms are quite different. So the standard Nitrogen boron pattern is over here, but in line A we start with 2 carbon atoms whose intensity is in between, and that's because the high angle dark field image has this kind of dependence on the atomic number Z. And oxygen is much stronger still, so we've got a monolayer, and just from the intensity of each atom, we can tell what kind of an atom it was. And there's also sodium down here. These atoms are actually sodium, and they're very saturated. And if you quantify that, so you do DFT calculation, and you superimpose the structure, and now you start seeing things like this carbon atom is actually pushed into this 6-fold carbon ring because the oxygen atom is a little bit bigger than the other one. So it pushes on this carbon atom, and the displacement is something of the order of 10 picometers. Knut was talking about how we can determine the displacement between the atoms to much better precision than the resolution that we have between 2 atoms, and that's nothing that has been done before. Astronomers typically determine the displacements to something like 1,000th of the width of the peaks. So if you have good statistics, you can do it. So this image, another kind of icon for what electron microscopy can do, got on the cover of Nature. So that was like a model getting on the cover of Vogue. That was kind of fun too. So this is what we could do for structural studies, but of course we didn't stop there. What can you do for elemental composition? If you take a high angle dark field image and you look at what signal came in the EELS channel from pixels on top of an atom, in between atoms, this one shows the bright atom. That was lanthanum, and there was also manganese in this spot. In the dark spot, that was titanium. And you can translate it into color-coded maps, lanthanum, titanium, manganese, and you can combine them into RGB, and you basically have the capability to map the composition of the sample at atomic resolution. Quite important, and elemental mapping has at atomic resolution has become everyday reality in aberration corrected STEM. And one more, so these gentlemen, I'm showing the results from Quentin Ramos. Boujou at Oak Ridge did a very similar thing, just didn't present it as photogenically as Quentin did. Theoretical spectra taken from a single silicon atom, 4-fold coordinated, replacing 2 carbon atoms in graphene. Good match between the experiment in line and the theoretical spectrum as solid. For the 3-fold case, so silicon can coordinate 2 different ways in graphene. Very poor match if the atom is forced to sit in the plane of the sample. If it's allowed to pop out like this, then you get a superb match. So you look at the energy loss spectrum. Here we're looking at the L23 edge, and you can tell what is the atomic environment around the atom. So the fine structure is basically electrons reflected from neighboring atoms influencing the shape of the edge. So that's quite wonderful too. Now, so atomic environment, single atom determined by EELS. That was just basic aberration correction. What can it do for us? How can we go beyond? 2 further milestones, a new type of a monochromator, ground potential monochromator, design presented in 2008 at the Royal Society meeting on new possibilities with aberration correction. I think all the aberration people, correction people in this room were at that meeting, right? So if I remember right. The translation of this design into mechanics, that was done by myself and George Corbin. And we also needed a new spectrometer to give us better energy resolution. Tracy Lovejoy led that project, and it was heavily inspired by a spectrometer which I developed at Gatan imaging filter. This one has had several followers, and I think Max's imaging filter is not that different from this concept, magnetic sector followed by lots of multiple lenses and good camera, piezoelectric operated slit right there. two things were important to add to the concept of the monochromator. One was to tie the monochromator to the spectrometer, and we did that quite simply by running one and the same current through all the prisms in both the spectrometer and the monochromator, and then to tie the spectrometer monochromator to the high voltage. And that is done by sensing where the zero loss peak is falling on the monochromator slit and tying that to the high voltage. When you combine the two, we expected that 10 millielectron volts resolution might be doable, but this slide is from 2008, and we have learned that we can do a lot better since. So aberration correction is important. We correct all aberrations up to third order in the monochromator here, and up to fifth order at the sample and in the EELS. So the whole system looks like this, and it has gone quite a long way beyond Crew's original STEM. And the results it can get is half an angstrom spatial resolution and 3 millielectron volts energy resolution. So I think I started about 5 minutes late. Do I get extra 5 minutes around it? 3 minutes. Okay, so we're going to have to negotiate. But yeah, I've got enough for maybe like 7-8 minutes. So progress in EM energy resolution. Without monochromators, cold field emission gun allows you to get down to 250 millivolts, and Chicago STEM already accomplished that. With a monochromator, a wonderful machine built by Zeiss with a CEOS Omega filter monochromator and Zeiss Mandel and EELS gave 43 millielectron volts. We have now got down to 2.7 millielectron volts, and the quest is on to get down to 1 millivolt. That would be wonderful for infrared spectroscopy. So that's nearly 100 times energy resolution improvement from this value and 16 times resolution improvement from here. So you would expect that a new world of possibilities would open up. With the imaging, we improved the resolution 5 times. With spectroscopy, energy resolution is improving 16 times. So let's have a look at what it gives. The most interesting region is going to be this energy region down here, where energy loss is previously hidden by the cold field emission electron gun. Well, tail of energy distribution completely hid them. So the 0 to 500 millielectron volts contains all kinds of vibrational spectroscopic signals and is of great interest. And this was hidden by the zero loss tail. So back in 2014, about a year and a half after these machines started working, we at Nion were wondering, somebody should have seen a phonon signal by now. And actually turned out that ASU did see the phonon signal, but people brought the spectrum to a well-known expert in energy loss, and he said, no, that's just noise, don't worry about it. So we came to ASU for a 4-day weekend session with a whole bag of specimens, and when we came out, we had spectra from SiO2, boron nitride, silicon carbide, that came from Phil Batson, titanium hydride, and epoxy, where we saw a hydrogen peak. So basically verification, yes, phonons can be seen in the electron microscope. And at the same time, there was a result from Japan. I think the pointer just went out. Excuse me, do we have a second pointer? This one doesn't. Oh, and how do I? Yeah, okay. So I have slight advance, but where's the laser pointer?
There's no laser on this one, I'm sorry.
Oh.
I will change the battery.
Oh, okay. Oh, okay, so 2 hands. Okay, thanks. Okay, wonderful. Yeah, okay. I think it should. Yeah, it's working. Randy, everything's fine. Yeah. So with the vibrational spectra, it's important to realize that there are two types of signals that we're actually looking at. Something that we call dipole scattering, which can be mediated by a virtual photon from some distance away. So you can have the fast electron go tens of nanometers, even 100 nanometers right from the sample. There's an electromagnetic wave surrounding the beam of fast electrons, and it's as though a virtual photon was interacting with the sample has to have polar moments in it. So if there are some plus minus atoms, it can interact at the distance. There's the other type of scattering is so-called impact scattering, which doesn't need any charges distributed in the sample. We interact directly with the nucleus, and therefore the scattering angles are much higher. So this one you can select by placing an aperture at a finite angle. This one you can select by sending the beam some distance away from the sample. And they have different stories to tell you. The dipole scattering, if I put the beam outside the one-in platelet like this, say 30 nanometers away from the edge of the platelet, we will get spectra that are essentially very similar to infrared spectra. And there's no radiation damage because we're not illuminating the sample directly. So you get spectra such as this. When we started the first paper, 2016, not such great energy resolution, about 9 millivolts. So we could see the peaks due to the hydrogen oscillation. So if you look around the molecule, all the white atoms are hydrogen, and the different peaks can be ascribed. The B, C, D, and E peaks in here come from these atoms vibrating. The strongest peak is oxygen vibrating next to a carbon atom. So that's the one at 205 electron volts. And then there's a whole bunch of transitions which have to do with oscillations in the 6-fold and 5-fold ring, which we weren't seeing initially, and we started seeing them later. So you can use this kind of capability for doing things like distinguishing between a L-alanine molecule where you have a 12 carbon atom in this place as opposed to 13 carbon. These are experimental spectra, not even smoothing. So we've developed nice ways of producing spectra that look like they came from theory. This is 100% experimental. There's a shift in that carbon-oxygen vibration by 4.8 milli-electron volts. And you can use it for mapping where the carbon-13 form of L-alanine sat relative to carbon-12. The spatial resolution is about 100 nanometers, but that's way better than what standard infrared spectroscopy could do for you. So isotopic substitution can be used to study metabolic pathways in cells and whole organisms. And two last examples. We can detect vibrations from a single stacking vault. This is work by Xing-Shu Yan and University of California in Irvine and his collaborators. But here you want the good spatial resolution, so you have to look for away from the 0,0 point in the diffraction pattern or gamma point in a Brillouin zone. So we look at the X point, and when you come to a stacking fault, the signal changes like this, and then you can produce a map with that kind of a signal. So we have distance to the stacking fault. Here we have a high-angle dark-field image. The resolution in the high-angle dark-field image is not 1 angstrom because we're also trying for good angular resolution to select the high-angle scattering. So you can't have the two. Quantum mechanics tells you you can choose one or the other, but you can't have both. And you can see that there's dramatic changes at the stacking fault in the phonon picture. And so what's happening, phonons are being scattered at the stacking fault, and this influences the thermal transport properties and acoustic transform properties of the material. And it turns out there is no other experimental technique to study this kind of thing. So we expect quite a few results from actual systems studying phonon interactions with defects. And my final example, again, going off axis to choose electrons that have been scattered by high angles. So here we actually do it by deflecting the beams of the bright field disk, misses the EELS entrance aperture. This is work by Quentin Ramos and Frederick H. at the SuperSTEM laboratory in Dasbury. Theory predicts that when you do this and you put the beam on a silicon, atom incorporating graphene, you will get a spectrum very different from the rest of the graphene. Experiment bears it out quite nicely. There's more background signal in here. I think they probably assumed that the probe was a little bit more ideal. Real probes have a little bit of tail, so there's a bit of signal coming from sites 1 and 2, adding themselves to the silicon. So the moral of that one is electron microscopes can now hear the tiny ping of one atom as it's vibrating. That's something, if you asked me 10 years ago, will we be at this point, 2022, I would say, wake me up. I must be dreaming about this thing. Okay, so conclusions. Electron microscopy has seen a lot of progress in the last 25 years. And aberration correction was one of the drivers, but for what we do, it was not the only thing. We have done other things as well. We have better electron detectors, sample stages, and software, and they have been key to improving the performance. And many people have contributed. So I showed you results from our instruments out in the field. We don't do all the experiments. We usually start them up, so the phonons, we basically said, hey, this should work, and we demonstrated that it does, and then the field took it over. And here's some of the examples that I showed you what can be done nowadays with electron microscopes. And it's a huge collaborative effort. We have a lot of people at Nion now. We've gone a little bit beyond the 3 guys who designed the first microscope, but here they are. That's the original Nion trio, and we did take on designing an electron microscope at that point. And we also have collaborators outside of Nion, so we had a nice open house just 4 weeks ago, and you can see quite a few characters from electron microscopy in the image. And we're all grateful to them, and thank you for listening, and thank you to the Kavli Foundation for making this whole thing possible.
Okay, should we have time for one question to Ondrej? It's very soon, or it's 5 minutes since lunch. Okay, Tom. Wait, microphone.
Thank you, and also to the others. These machines, which have been created with a lot of sweat and effort and persistence, they are now around all across the world. And so how many machines are there?
50 monochromated instruments of this type now.
Yeah.
2 in Beijing, going up to 4, I think, and about 5 in the States, and something like 5 in Europe, maybe 6.
So it is becoming accessible.
I think so.
Yeah.
So like Quentin Ramos runs a user facility. Send me an email, he will schedule you. You get 1 day for free just to look at your samples. And if it looks promising, then he wants some funding.
Yeah, thank you, Ondrej.
Okay. Well, thank you very much,
Small
Randy.
gift from NTNU.